Okay, so here we are looking at when derivatives fail to exist. I think at this point, based on the last video, you could probably negotiate these limits and kind of decipher a little bit how they come to be. But if we were to look at this first instance where we have something called a corner, we use an absolute value function to show an example of this in practice. If you look at the proof of this, we're looking at the limit as h approaches 0, and you notice we have to do this from the right and from the left again, like we did in the last one with the piecewise function. And the reason why we're doing that is that, remember, whenever we have an absolute value function, we want to break that apart into a piecewise function. And so the limit definition of a derivative is going to have to be done both as h approaching 0 from the positive and then h approaching 0 from the negative. And as you guys follow through that limit, you can kind of see in one case we're approaching positive 1, and in the other case we're approaching negative 1. I think the video, or not the video, the illustration on Desmos probably shows us a little bit of a better picture of what's going on to justify kind of like this approaching 1 and approaching negative 1 from either direction. So if we just take a moment and go to Desmos and take a look at that absolute value function, we can kind of see pretty clearly here that the left of the corner, so the corner that we're interested in is that value of the derivative when x is equal to 2. And if you look anywhere to the left of it, that piece of the line has a slope of negative 1, which is never going to change. It's not changing towards any particular different value. It's going to stay negative 1 from the left. But from the right, you have a slope of positive 1. And again, that's not changing. And so the negative 1 is approaching, you're approaching negative, or you're at negative 1 from the left, and you're at positive 1 from the right. Those aren't going to converge to any kind of particular same value. So therefore, the limit does not exist at that point 2 comma 0. And again, it's what we call a corner. The next case of a derivative not existing is when a function has a discontinuity. And we actually just saw that. That was the segue problem. So this is just another example of the same situation, where if you ever have a point of discontinuity, the derivative simply cannot exist. You can't even draw a tangent at a point that doesn't exist on the function itself. So the whole idea is just kind of impossible to do. But again, if you want the justification, you can go back through that limit as h is approaching 0 both from the left and from the right, as you kind of see in the notes already. One note to kind of make here, I'll go back to Desmos, I suppose, with this one. I believe we can already understand what's happening from the last video. It's the same situation. So the one example I didn't really show, though, is these are both jump discontinuities. The one I did in the prior video and this one as well. If a question's coming up about what about a hole where the limit exists as you approach that value, what you have to keep in mind is that we're not finding the limit of the function. We're finding the limit of the slope of the tangent. And so since that's the limit that we're trying to find, we have to be able to be defined at the point of tangency. And so if the function itself has a hole and it's not even defined at the point where we want to explore a tangent, then there's no way to draw anything there or pursue it. It's in an impossible situation. And so therefore, even if there's a hole there, you're still not going to have a derivative existing at that point, but definitely not at a jump discontinuity. Finally, the third case which we take a look at is having what's called a vertical tangent. In other books, you might see this being called a cusp. And this is a situation where the limit can be evaluated, but as you evaluate the limit, the definition of it is that if we take the absolute value of the derivative as x is approaching a, the limiting value of the slope is just going to approach infinity. We're just taking care of both the positive and negative cases all in one. And remember, vertical tangents we don't really have a definition for because slopes of vertical lines are undefined, and so the derivative, showing the slope of a tangent, well, if that slope is tending towards a vertical line, then the slope is undefined and therefore doesn't exist. And so the derivative wouldn't exist if we have a vertical tangent. Again, I'm going to leave the limit for you guys to kind of look at. Everything's pretty much straightforward as you're looking through the pieces here as you explore the justifications. But if we kind of go to the picture to explore what does a vertical tangent look like in practice, or a cusp. I want to show that over here and go to that function. So we see this one, function green here, and I'm going to try to make this a little bit more defined because some stuff is happening here that you might want to differentiate between this and the absolute value situation. So recall with absolute value, we call that a corner. And we call that a corner because the slopes actually coming from the left and the right are fixed. You know, that's -1 from the left and +1 from the right, and it's not changing at all. That's a constant slope. As opposed to what you see in green, you know, you can start looking at the slopes of tangents. Imagine that from the left and from the right. But what's happening is that if you imagine it from the left, you actually are getting slopes that are negative, but they're negative and they're getting steeper. And if we kind of look at this and watch this and play a little bit closer when we're zoomed in, you can kind of see that from the left, the tangent's going to get very, very steep negative, thus approaching kind of like this negative infinity from the left, if you can imagine that. Whereas from the right, you have a positive slope, if you imagine the secant, drawing closer and closer to that point of tangency that we were considering at x = 1. And you see that that would also go vertical, and we'd consider that to be a positive infinity. And so if we go back to the definition, we can see that this is why they kind of pursue this definition as an absolute value of the derivative as x approaches that point of tangency that we're trying to consider. And we're just going to say the definition is that if we show that the absolute value approaches infinity, it doesn't really matter if it's positive or negative. That tangent is approaching something that's vertical and that's undefined, and so therefore the derivative fails to exist at that kind of situation as well. And the conclusion of this effectively is continuity definitely is required for differentiability. However, there's also cases where you're still continuous and you're not differentiable. So if we go to the corner, remember the absolute value function is continuous. However, at the corner, it's not differentiable. So continuity is not everything for differentiability. Same thing with the vertical tangent. With the vertical tangent, we are defined here. X can equal 0, or x can equal 1, that's fine, you're continuous. However, you definitely don't have any kind of differentiability there because of that vertical tangent. So the conclusion is that a function, if you read at the bottom, it's that is differentiable at a is also continuous at a. That's a guarantee. So if we're being told that a function is differentiable at a or at all values of x, then that's enough to tell us that the function is continuous. The converse is not true though, and I just brought up those cases that you have to think about where just because you have continuity does not necessarily mean you have differentiability, with the corner and the vertical tangent being those two cases that you need to consider. So that is some important information with derivatives, that we have our definition of a derivative, but we also got to realize that just because we run through the limit process does not necessarily guarantee we're going to end up with a actual value for that derivative at a specific point where x = a.